Most electrical circuits we've encountered involve direct current, which flows in a single direction. But the energy in our homes and offices is different. It is alternating current, or AC, where the flow of charge reverses direction rhythmically. This alternating system dominates our modern world because it is highly efficient. Using transformers, AC voltages are easily converted to higher or lower levels, allowing power companies to transmit electrical energy across long distances with minimal loss. This entire electrical infrastructure is built on the work of Nikola Tesla. He conceived of the rotating magnetic field, the foundational principle behind almost all alternating current machinery used to generate and distribute power today. We describe this alternating voltage mathematically as a sine function. It follows the formula V equals Vm sine omega t. The value Vm represents the amplitude, marking the maximum potential difference, the crest of the wave, before the voltage drops to zero. This leaves us with a unique problem. If the voltage constantly swings back and forth, how does it interact with a basic resistor? To find out, we look at a pure resistive circuit. In this setup, an AC source is connected in a single loop to a resistor, with no other components to complicate the flow. By applying Kirchhoff's loop rule, we know the sum of potential differences in this loop must be zero. This means the voltage across the source is always equal to the voltage across the resistor. Since current is simply voltage divided by resistance, we can derive a new equation for the flow. This gives us I equals Im sine omega t. Here, the peak current, Im, is determined by dividing the peak voltage by the resistance. This shows that Ohm's law remains valid for these peak values, just as it does in DC circuits. In a purely resistive circuit, the current doesn't lag or lead. It is forced to follow the exact mathematical timing of the applied voltage. When we plot these together, the relationship is clear. The larger blue wave represents our voltage, and the smaller silver wave is the resulting current. Both waves cross the zero line at exactly the same time. There is no delay. The current responds to the voltage instantly. They also reach their maximum and minimum points in perfect synchronization. Engineers describe this state as being in phase. In a resistive AC circuit, current and voltage work in a perfect rhythmic alignment. This creates a mathematical puzzle. Because the current spends half its time flowing forward and half its time flowing backward, the average current over a full cycle is exactly zero. But if the average current is zero, we might assume no work is being done. Yet we know that a light bulb connected to an AC source still glows and produces heat. The answer lies in how heat is produced. Joule heating is proportional to the square of the current, I squared times R. As this graph shows, when you square a negative value, it becomes positive. This means the I squared value stays above zero throughout the entire cycle. Because the squared current is never negative, energy is dissipated as heat during both the forward and reverse strokes of the AC cycle. To calculate the actual work being done, we need a measurement that accounts for this effective heating power rather than the simple average. This measurement is called the root mean square current, or RMS. Think of the RMS as the effective current. It represents the amount of steady DC current that would produce the same heating effect as the alternating current in that same resistor. Mathematically, RMS is the peak current divided by the square root of 2, roughly 70.7% of the peak. Applying this to voltage, we can use familiar DC formulas for power and Ohm's law. With RMS, AC math becomes as straightforward as DC. This is why almost all AC measurements are given in RMS. It provides a practical baseline for the work the electricity can actually perform. For example, the standard 220-volt rating for a home outlet is an RMS value. If you were to look at the actual peak voltage of that 220-volt supply, you would find it reaches approximately 311 volts at the top of its wave. The root mean square value allows us to ascribe the complex, reversing flow of alternating current with the exact same clarity as a steady battery.